Okay, so let's do a quick review of what we've got on these slides. We went over this, so I'm not going to do that one. Most important, we went over these, and I think the last one is where we kind of got, yeah, okay. So then I've got answers for the rest of these. All right. So where does the diaphragm connect? Well, it makes, pretty much a seal for the entire thoracic cavity. So it's going to connect at the very bottom of the rib cage. So all along here. Also the lumbar vertebrae in the posterior portion of the diaphragm is going to connect to the lumbar vertebrae. And then right here, the diaphragm connects to the xiphoid process of the sternum. What direction do the fibers of the diaphragm pull? Well, they're all going to pull, like as a whole unit, they're going to pull in all directions, because you've got your central tendon right here, and then the outer wall of the diaphragm is all around, and so they're going to kind of all pull out like that. And what it's going to do is bring the diaphragm from a domed shape down, right? So it's going to pull in all directions to bring this down. There are some major muscles of inspiration that you have that are not the diaphragm. Those are the sternocleidomastoid right here, pectoralis major and minor, serratus anterior, which is right here, and some of your intercostals, but you've had these in the lab and in class, so I'm going to let you find which intercostals are important for inspiration. You'll also need to know which are important for expiration. What keeps the torso rigid during breathing? That's the erector spinae group back here in the back. You don't need to know all the individual ones. You can, but I'm not going to ask you for them individually. How are the intercostals arranged? Like this, right? So you've got some going this way, some going this way, and then you have that other group, the innermost intercostals, which are arranged like this. So you've really got like three different directions. This is important because it kind of makes like a weaved, they're not weaved, they're not interweaved like that, but it does have this kind of like lattice structure that creates a really strong wall, basically. So you have a very strong wall of the rib cage, which is great for those pressure differentials that you need for breathing. So that's great. Flail chest, that's up to you to figure that one out. Muscles of expiration, you're going to have the abs, the obliques, and some of your intercostals. But again, which intercostals? How do the obliques tighten the sides of the abdomen? So they're, well, I'd have to stand up, and I'm just wearing basketball shorts because I'm at home today, so I'm not going to do that. Anyway, so the sides of the abdomen, right? The obliques are going to tighten those. How do they do that if there's no bone to pull against? Like, they do connect back here to the spine, to the vertebrae, but in the front, there's nothing to connect to. So how can they tighten the sides? It's because of the linea alba, which is tissue that runs from connective tissue that runs from the sternum to the pubic symphysis, right at the very top edge of the pubic bone. So it's like a very stiff structure. I mean, you can kind of feel it if you tighten up. You can like press against the linea alba. It is what creates the line between like your 6-pack or 4-pack or 2-pack or whatever you've got. But the line, the vertical line that cuts between those muscles, that's the linea alba. Okay, what can aid in exhalation aside from muscular contraction? So if we want to blow out like that, we're going to tighten up some intercostals, some abs, etc. But if we want to just breathe out, we've got gravity, which is going to pull down on the rib cage, and we've also got elasticity, which is going to, like the recoil of the elastic tissue that we've spread out to take in a breath, right? So the lungs are stretched all the way out. They kind of want to contract back to where their resting state. The same for all of the muscles that are stretched out. So you've got other muscles and tissues that are being stretched by tightening of the inhalation group, and they want to go back to where they were. So recoil and gravity. What happens to thoracic cavity pressure when the diaphragm relaxes? We talked about this at the end of the like half of the review yesterday. But it increases when the diaphragm relaxes. It increases. If you want to see a longer discussion of that, I'm going to post. It should be up right now. The beginning part of the review in class should be up. Okay, bones. There's a couple things. Oh man, I'm over top of my joke. If anybody has watched this movie from the early 90s, Kindergarten Cop. I don't remember. I was a child. I really liked it. Who knows if it holds up? Anyway, what are the vertebral divisions and how many vertebrae in each? Well, remember, you've got cereal at 7, tacos at 12, lasagna at 5. Cervical, thoracic, and lumbar. So you've got 7 vertebrae, 12, and 5. Why is there an inverse relationship between the vertebral foramen, so the whole, and the vertebral body, which is the actual osseous portion of the vertebra? So at the top, you'll have a large foramen and a small vertebral body. And then down towards the bottom of the body, you have a very small foramen and a very large vertebral body. This is because the spinal column goes through that vertebral foramen, and the further you go down the body, the less nerves there are in the spinal column because they've all branched off to go to things, right? Just like if you're on a freeway that is getting to its ending point, it starts, there's fewer and fewer lanes. They've all kind of branched off to go other places. Then you're down to one lane, it turns into like a little highway, and then it's no longer divided. Now it's just like a road, right? So that's kind of what's going on there. You don't need as much space. Also, the vertebral body is larger there because the further down the body you go, the more weight each vertebra is carrying. So you have to carry the body, and you have to be able to carry anything that the body carries as well. So anything that you're picking up, sitting on your head, whatever, all that kinds of stuff, it needs to be able to hold that up. So that's the inverse relationship there. The atlas, there's the joke from Kindergarten Cop. You can see the parallel. C1 is the atlas. It's the first cervical vertebrae. It's called the atlas because it holds up the head. In Greek mythology, Atlas holds up the earth. I assume that Greek mythology is still something that's taught in schools, although if it's not, maybe you don't get it. One of its things is it's got two main things that it does. The atlas interfaces the skull with the spinal column. And then also it does not allow the skull to turn too much, right? There's like little facets on the atlas that allow the skull to turn so much, but then it runs into a larger, we'll say a cornu. It's not exactly a cornu, but it's a portion of bone that sticks up that the head then runs into and can't turn too much. If the atlas was damaged in some way, this wouldn't be good. The head could turn too much and it could damage the spinal cord. How do the ribs connect? Well, the ribs connect to the vertebra, right? Well, the ribs also connect to the sternum in the front. Some do. The number of connections for each rib on the back in the spine, which is what I meant by this question, is there are 3 connections. You're going to have 2 connections on the corresponding rib and 1 on the rib above. So on the corresponding rib, you have the superior costal facet and the transverse facet. And on the one above, you have the inferior costal facet. So 2 connections on the corresponding rib, 1 connection on the rib right above, which means that the very first rib is actually going to touch the vertebrae above. So it's going to touch a cervical vertebrae instead of a thoracic vertebrae. All right. Where was I? Parts of ribs. Okay, so we talked about this. There are a few different parts of the ribs. Remember, there's the osseous portion, which is over here, and also in the back. There's the cartilaginous portion, which is this more front part. Starting about right here, you've got more cartilage in there that's connecting to the sternum. You have 7 true ribs. So the first 7 are true ribs. They go from the spine and connect directly to the sternum. After that, 8 through 12, those are false ribs because they just connect to the cartilaginous portion of the rib above. So right here, you can feel it, right? If you like take your hands and press in on your ribs, you can feel that they don't really connect to anything. You just have to walk it up until you get to the xiphoid process here. And then the last 2 of those false ribs, 11 and 12, are floating ribs, which don't even connect to the next 2 ribs above, or to the cartilaginous portion of the ribs above. I'm not 100% sure I can... Oh, yeah, there they are. So you can feel those too, way down there. So 1 through 7 are true ribs, 8 through 12 are false, and 11 and 12, even though they're false ribs, are also floating ribs. So they're floating and false. What are the sternum sections? You've got the manubrium. That's the handle. So if you look at it, it kind of looks like one of those old Roman swords. So you've got the manubrium, the gladiolus, which is like the actual blade part of the sword, and then the xiphoid process, which is the pointy part. All right. Where do the ribs connect? Well, the first and second ribs connect to the manubrium. The first one goes right on the manubrium. The second one actually touches the manubrium and the gladiolus, and that's why you see that 2 through 7 touch the gladiolus. So 2 is on the manubrium and the gladiolus. Next. Okay, airway. What is the air tube? The trachea. And the bronchi. And the bronchioles, right? So it's trachea, and then it's bronchi, and then it's bronchioles, where it gets kind of very small. The rings are made of cartilage. The rings of the trachea are cartilage, and they're, remember, like cheap jewelry. There's no, I'm not actually wearing any, so I don't know why I did that. But they don't connect in the back. And this is great because then they can flex. They won't break like a plastic straw does if you bend it. It would be terrible if our trachea did that. But they don't flex too much so that it can collapse. It adds just exactly the perfect amount of stability. At the end of the tubes are alveoli, and those help with gas exchange. They're what oxygenates the blood. They do that so well because of so much surface area. Each little round alveolus increases the surface area by a ton. If you have, so if that's a concept that's hard to understand, which I don't know if it is or not, think about a golf ball. So think about a ping pong ball. It's very flat everywhere. And then think about a golf ball, which has all these little dimples in it, right? And so if you were going to, there's so much more material on the outside of a golf ball because it goes into these like little divots. Of course, the alveoli go out and they create larger divots, but still that just uses up more surface area. So it's really increasing the surface area in the lungs and putting the entire amount of the body's blood all over all these alveoli to allow for oxygen to move into the blood. Okay, not at once, not putting the whole body's blood at one time, because of course some of it is still in you in other places, but it's really effective at oxygenating large amount of blood. I think I'm not gonna. I used to know the amount. It's not important for the exam, but I wish I still knew it. Okay, what aspect of speech can airflow modulate? Loudness. We talked about how it can modulate pitch a little bit, but the one that I really want you to know is loudness. We've got subglottal pressure down here, and we've got intraoral pressure right here. So there's two different speaking pressures that we can measure. Our typical inspiration-expiration rate is 40-60, 40 inhale, 60 exhale, and 12 breaths a minute. When we start speaking, though, that goes to 10% inhale and 90% exhale. But it's still roughly about 12 breaths a minute. Depending on how loud you're talking and how animated you are with your speaking, that can go up. But a typical quiet conversation is still 12 breaths a minute. What about when you're not speaking, but you are in a conversation, so you're listening? Well, then your breathing starts to mirror the person who is talking. And theirs mirrors yours when you're talking. When we are speaking, we're using the inspiratory reserve volume, the tidal volume, and the expiratory reserve volume. We go up above where we typically breathe in. We use all that typical amount, and then we also go below what we typically exhale. What muscles are used in speech? All of the inspiratory and expiratory muscles are used in speech because we have to breathe in more than we usually do just with quiet breathing, and we also have to exhale more than we do with quiet breathing. Here's a question that I won't answer for you though. What do you use to hold your breath? What muscles do you use to hold your breath? So you breathe in, hold your breath. What muscles are you using? Okay, coordination and cognition. This is the last one. During high load questions, we typically hold our breath. And during low load questions, easy questions, we'll usually breathe out. So people ask you like, what'd you eat yesterday? Oh, food, right? What's 633,000 squared? And then you hold your breath. What is typical of speech breathing in Parkinson's? Well, a breathy or creaky voice is typical for breathing with Parkinson's. That's as deep as you need to go into it. We will definitely hit on that more when we actually talk about phonation. But for now, all I really want you to know is that it's hard for them to control the rate of breathing out because they're not able to control the subglottal pressure because they can't control the vocal folds, and it creates a breathy or creaky voice. How do we coordinate breathing with what we're going to say? Well, larger inhalations come before longer speech. And we also inhale at natural pauses. Like right there. There was a period in that sentence. So what does that mean for what we've planned in speech? It means that we kind of have an idea of what we're going to say. Like we have an idea of how long what we're going to say is, even if we don't know the exact words. So is this going to be a short answer or a long answer? Are we just kind of like shooting the shit, and like talking? And so I know that I'm going to tell you this really funny story that's kind of long. So taking a big breath. Or if I'm listening to a funny story and I might want to interject a question or something, I'll take in just a little breath to say like, oh, he did not. No. What? Like that. So we kind of know, even if we don't know the word that's coming out yet, because that's still kind of like in process, and sometimes until the motor program is initiated, we have some idea of what the length is going to be. Okay, that's it. Any questions? Email Corelli, email Lexi, email me. This will open for you on Friday at probably 9, but it could be 9:30. If there's some sort of issue with it, it'll be 9:30, but it'll probably be 9 o'clock. All right. Good luck.